Okay, guys, I want to do 10.3 with you. In 10.3, we kind of go back to understanding how to work with radicals. In 10.2, we learned how to handle fraction exponents. So now we're going to kind of go back to radicals for a minute and learn how to multiply them and divide with them. So you've got two rules for radicals. You've got the product rule. I can only multiply radicals if they have the same number in the little corner of the radical, so the same type of radical. This is like the nth root and the nth root. So since they're both the same type, I can multiply whatever's under this one with whatever's under that one, as long as they're the same. So I wrote that over here for you. I can multiply radicals if they are the same type of radical. Okay? And the quotient rule tells us that if we have a fraction under the radical, we can apply the type of root, the type of radical to both the numerator and the denominator. This is really interchangeable. So you should use whichever rule allows you to simplify the most. Whenever you have a problem like this, think about which form are you going to be able to simplify the most. And that's the form you should go with. Okay? So we're going to do some examples. This is not going to take very long. This is a shorter lesson. So we're going to do a few examples here to make sure we know how to handle both of these rules. Okay? So the first one is going to be the fourth root of AB squared times the fourth root of 27AB. So I see that I have the same type of root. So since these are the same, I know that I can multiply whatever is underneath the radical. So this is going to give me the fourth root of 27. A times A is A squared. B squared times B is B to the third. Okay. Now I have to check this out and see if I can simplify further. But since it's the fourth root, I know that I have to have 4 factors or 4 variables in order to take out a group. Well, I know that 27 is 3 times 3 times 3. You get kind of used to that in this chapter. So I know that I don't have a group of 4. It's just 3. So I can't take anything out. And I definitely don't have 4 A's or 4 B's. So can't take anything, can't simplify further on this problem. I would have to have groups of 4, and I just can't do that. So you do have to check and see. But in this particular example, there was nothing more that I could do. Okay, so let's keep going. Let's see. And I will scan this and post it as soon as I'm done with the video. Fourth root of 27. I know I'm doing fourth root a lot. We'll do some more in a minute. But it's just to teach the concept. Okay, so the fourth root of 27 and the fourth root of 3. So I know I can multiply those. 27 times 3 is 81. Now with this problem, I can go further because I know that the fourth root of 81 is 3. So that's my answer here. If you need to be reminded why, it's because we know that this is 9 times 9, and I've got those 4 3s, right? So hopefully we are kind of understanding this rule. I think sometimes it's just because it looks weird. Like, for instance, you may see a multiplication problem like this. 6 over m times n over 5. But they're under the square root. I know these are the same type of root because it's understood to be a 2 there, right? So I know that I can multiply these because they're both square roots. I can't do any, there is no square root of 6. There is no square root of 5. So the only property I can apply here is to multiply them and put them under the same radical. So that's just going to be 6n over 5m. And that would be it for that problem. I can't do anything else. So they will try to trick you. All right, let's look some of the quotient rule. Let's do something. Let's do the square root of 6 over 49. So square root of 6 over 49. So I know that I can use this interchangeably. It's going to work to my advantage because if I split it up, I can treat the numerator separately from the denominator. And that helps me here because in this denominator, I have the square root of 49. And we know that that is 7. So see, it helps me simplify it further if I write it as 2 separate radicals. I can't do anything with the square root of 6, so it just stays square root of 6. That's okay as long as the radical's in the numerator. You can leave a radical in the numerator. Alright, let's look at just a few more. So let's say we had the 4th root of y over 81 to the x fourth. 81x to the 4th. Sorry. Well, I definitely think it's going to be good to write this as 2 separate radicals because I can't do anything with this as a fraction. I can't cancel anything here. So it just works better to write it as the 4th root of y over the 4th root of 81x to the 4th. And I can do that. I can do stuff here because I know by now that the 4th root of 81 is 3. And if I have 4 x's, I can take all of that group out and represent it 1 time with 1 x. So this is going to be the 4th root of y, because I can't do anything with that. But on bottom, this is going to be 3x. 4th root of 81 is 3. 4th root of x to the 4th is just x. All good because I don't have a radical in the denominator anymore. Alright, well I'm going to show you one next that actually helps to look at it together. Sometimes they will give it to you separated. So a to the 7th, b to the 6th over a to the 3rd and b squared. Okay? See, this one I think is better to write as one big radical because I know that if I have the same base, I can subtract exponents. So for this problem, I would rather look at it this way, with everything under the radical. Now I can see that this gives me the square root of a to the fourth, b to the fourth. And then I can do more with that because this is groups of 2, right? Because it's a square root. So this actually becomes a squared, b squared, everything outside of the radical. Square root of 4 is 2, right? So our 2 groups of a's and 2 groups of b's can come out. So that would be your final answer. I don't want to show you one more. This one has a little bit more to it, but it's also another example of looking at it as one big radical instead of 2 separate ones. I'm doing a lot of fourth roots today, but so fourth root of 160, x to the 10th, y to the 5th, over the fourth root of 2, x squared, y squared. Hopefully you can see that this is going to be another problem that's best to look at as one whole fraction under the radical, because I can subtract these exponents and I can divide here. So this is another example of a problem that's better to work out with the whole fraction under the radical. This is going to give me 80. 160 divided by 2 is 80. 10 minus 2 is 8. 5 minus 2 is 3. So now I just have to simplify this radical. So this goes back to 10.1. In 10.1 we learned how to do this. We've got to have groups of 4 when I do my factor tree here, and I've got to have groups of 4 with these variables. So I know I've got 2 groups of 4 in my x's. So those are going to be able to come out. I don't even have a group of 4 with my y, so that's going to have to stay in. But I also know I need to do a factor tree for 80 and figure out what I have. 10 times 8, and then I break down the 10, 5 and 2. The 8 is 4 and 2. I need groups of 4. And here's my group right there. So there's 4 2's. This is the only thing that has to stay in. So the answer here, a 2 can come out. Remember, we have 8 divided by 4 is 2, so I can take out x squared. And then I have the fourth root. The 5 had to stay on the inside, and the y cubed had to stay on the inside. So that would be your final answer for that example. Alright guys, well that concludes multiplying and using fractions underneath radicals. Multiplying radicals and fractions underneath radicals. I'm going to scan and post these, and I'll be back soon with 10.4.